Okay, in this video we're going to talk about converting between numbers and different bases. There's a section here about bases. We've done a number of examples, but now we'll explain why this stuff works. So we'll start with looking at base x numbers, where x is 2, 8, or 16 for all of these. 8, 16, or 10. 10 is what we're used to, so we'll start by looking at regular numbers. Alright, we're going to see how this works. So we'll start with decimal. Decimal is base 10. And what does that actually mean? So let's say we have a number like 234. So there's various things that could mean, but when we write 234, the 4 here we call the ones digit, and the 3 we call the tens digit, and the 2 we call the hundreds digit. Okay, and what this means is the 4 here really means 4 times 1. The 3 really means 3 times 10. And the 2 really means 2 times 100. Okay, and then the actual number is adding those all up. That's what 234 means. And you'll notice that the things that we multiply by here, the places, we have 10, we have 100, and 1. Those are all powers of 10, increasing powers of 10. 1 is really 10 to the 0 power. Any number to the 0 power is 1. And then we have 10 to the 1 power. And then we have 10 squared. And if we went up to the thousands place, that would be 10 cubed. So we'll look at what if we had 234 and instead of base 10, we were thinking in some other base. An easy one to think about is octal. So if we have the octal number 234, that's base 8. What would it mean? Basically, we want to do the same thing we did over here with base 10, except we replace all the 10s by 8s. So this 4 is going to be the ones digit. The 3, instead of being a tens digit, what should it be? Instead of a tens digit, it should be the 8s digit. And the 2, what should it be? With decimal, it was the hundreds digit, which is 10 squared. So now it should be, instead of 10 squared, it means times 8 squared. So it's the 64's digit. So this number here would mean 4 times 1. And then from the 8th place, you'd have 3 times 8. And then from the 64's place, you would have 2 times 8 squared. And then we would add all of those up. So we have 2 times 8 squared, 2 times 64, plus 3 times 8, plus 4 times 1. So if we convert that to decimal, 234 in octal, so 234, we'll put in a subscript 8 there to say 234 in octal is equal to 156 decimal. And if you want to check, there are various places you can go to check these things. Here's one where you can put in a number of some kind. it'll convert it for you. So we had 234 is 156. Now as a simple test, what would be 10 octal? If we convert 10 octal to decimal. Well, if we are over here, that would mean that we would have a 1 for the 8th place and a 0 for the 1's place. So if we did just replace this 3 with a 1, you'd have 1 times 8. So if we convert 1 0, it's 8. What about if we convert 1 1? Then this 1 is the 8th place, and this 1 is the 1's place, so it would be 8 plus 1. How about if we had 2 1? We would have a 2 for the 8th place and a 1. So we'd have 2 times 8 plus 1. That should be 17. Okay, that is converting from octal to decimal. Okay, what if we had base 16 instead of base 8? So let's say that now we have base 16, which is also called hexadecimal. So we have 234. If we're taking that to be a base 16 number, now we want to do everything with 16s instead of 8s or 10s. This one here is the 1's digit. It's always the 1's digit. And then the next one is always whatever base we're talking about. So that would be the 16's digit. And then you go up by powers of 16. So this would be 16 squared. That's what the 2 is multiplied by. And 16 squared happens to be 256. So if we look at what this number means, we have 4 times 1, 3 times 16, 2 times 256, and then add those up. We can add those up over in calculator. So 2 times 256 plus 3 times 16 plus 4, 564. So 234 as a base 16 number, if you think of that as a base 16 number, it's 564 as a base 10 number. Alright, now let's look at the 1's place. For base 16, so normally, and let's look at base, so let's look at the 1's place. Okay, so in base 10, what are the possible values for the 1's place? You have a digit, so you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the possible values for a digit. And then if you need to go past 9, then you would go 10, and you'd be using the 10's digit. Now in base 16, you need your 1's place to go up to, instead of going up to 9, what do you think the 1's place has to be able to go up to in base 16? It needs to be able to go up to 15, because if we put a 1 here in the 16's place in base 16 is worth 16. So we have to be able to get up to the number 15 somehow, and we can't use this digit here, the second digit, because that's already worth 16. So we have to be able to get up to 15 just using the ones place. So that means we need extra symbols. So we need to have A, B, C, D, E, F. And what these mean in base 16, A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. So when we get bases higher than 10, we need to have extra symbols, because you have as many symbols as whatever your base is. Okay, so now we can have things like, we're still in base 16 here. Now we could have a number like 2, 3, 4, we already did that. But we have other symbols that can be used. So we could have a number A3. And in base 16 in programming, it will be written 0x. So if we have 0x before a number in programming, that typically means that we're thinking of it as a base 16 number. So 0x, base 16, what is this 3 called? That's the ones place. What is this A called? That's the 16's place. So if we write this out, we have 3 times 1, and then A times 16. But what is A equal to? I had A, B, C, D, E, F going from 10 up to 15. So this A here is really something with the value 10. So A3 would be 10 times 16 plus 3, 163. An important example is FF. If we have 0x FF, what is this equal to? So this F here is the ones place, so that's going to be the value of F. F is worth 15, so 15 times 1. The second F is in the 16's place. F is worth 15, and we multiply it by which place it's at. So we have 15 times 16 plus 15 times 1. If you add that up, it's 255. And that's a value that tends to come up in programming in HTML. In colors, you'll often have red, green, and blue values that go 0 to 255. And if you write those in hexadecimal, that's from 0 to FF. Alright, let's go to, that's base 16. So we can take a base 16 number and convert it to decimal just by writing out the powers of 16 and adding them up. Let's look at base 2, which is called binary. Okay, the number that we started with for the other examples was 2, 3, 4. Question: does 2, 3, 4 make sense as a binary number? Base 2. The answer is going to be no. That's not a base 2 number. Whatever your base is, that's how many digits there are supposed to be. So in base 10, there are 10 digits, 0 up to 9. In base 16, there were 16 digits, 0 up to 9, and A through F. In base 2, there should be 2 digits, 0 and 1. So in binary, or base 2, it only makes sense to have numbers that are only made out of zeros and ones. And a lot of times there will be a B written after that to say that we're thinking of this as a binary number. Now we think of this just like we did with base 10 or 16 or base 8, but now we're doing everything in terms of 2's. The first place here is always the ones place. What is the next place called? It's the base that we're talking about. So if we're talking about base 2, that is the 2's place. What about the next place? We go up by powers of the base. So this would be the 4's place. And the next one would be the 8's place. And the next one would be 16. So this is the same as any of the other bases. You take the digit that's there. We have 0's and 1's. So this would be 0 times 1. That's what that first bit is worth. Then the second one here, there's a 1 times 2. And we're going to add all of these up. The next one here, we have a 1 times the place that we're at 4. The next one is a 0 times 8. And then the last one finally is 1 times 16. So if we add all those up, we have 16 times 1, we have 1 times 4, and we have 1 times 2. So that's going to be equal to 22. And we can check that. We can ask Google, convert 22 to binary. 10110, and they have a 0B before it. 10110. Okay, let's try another one. We're still in base 2. 1111. Put the 0B like Google did. So what is this equal to? This is a value that comes up in programming. So we have a 1 in the 1's place. We have a 1 in the 2's place. We have a 1 in the 4's place. And we have a 1 in the 8's place. So this is going to be equal to 8 plus 4 plus 2 plus 1. If you add that up, that is 15. And that also happens to be F from hexadecimal. So the largest digit in hexadecimal is equal to 4 1's in binary. And that is a useful piece of information because that ends up being that each 4 bits in binary is equal to 1 digit in hexadecimal, which we'll see in just a second. Another example that's kind of important, 0B111. So now we would have a 1 in the 1's place, a 1 in the 2's place, and a 1 in the 4's place, and that would be it. We add those up, that's equal to 7. And 7 is the largest digit in base 8. F is the largest digit in base 16, and 7 is the largest digit in base 8. So here we have 3 bits in binary is corresponding to 1 digit in base 8. So why base 8 and base 16 are important? If we want to do a conversion from binary to octal, our hexadecimal. Let's just say we have something like 110101. Okay, so if we want to convert that to octable, what ends up being true is you can take 3 bits at a time. 101 as just if we were just looking at that part of the number, we'd have this is the 1s, this is the 2s, this is the 4s. 4 plus 1 is 5. If we were looking at the second part as just its own part, we'd have this would be the 1s, this would be the 2s, and this would be the 4s. 4 plus 2 is 6. It ends up being true that 110101 in binary is 65 in octal. And in programming, a lot of times, if there's a 0 before the number, you think of it as an octal number. And you could check this by viewing this as a decimal number. Convert this to decimal. This is something you can do to check. Right, so convert that to decimal. Convert this to decimal. And you should get the same answer. Alright, hexadecimal is supposed to be 4 bits at a time. So we start with the same value, but now I want to draw a box around 4 bits. Now I only have 2 bits left over, so I'll put zeros there just so that I have it neatly as 4 bits. Alright, if I'm looking at these 4 bits, then this would be the 1's place, 2's place, 4's place, and 8's place. So that is 5. I would write that down. The next 2 bits are 1. That would be the 1's place, 2's, 4's, and 8's. 1 plus 2 is 3. So if you convert this binary value to hexadecimal, you get 35. And again, you can do this yourself, convert this to decimal, and you should get the same value. Alright, let us check our study guide. So what we've done is an algorithm from base 2, 8, and 16, converting that to decimal, we can do. And converting between binary and octal or hexadecimal, we can do, just by grouping the digits. So the part that remains is to convert from decimal to base 2, 8, and 16. There's a couple different ways to do that. Let's see, how are we doing on time? Go ahead and stop there and start a new video for that part.